Okay, dear students, another lessons about Kirchhoff rules. So this is book, recommended book is Physics for Scientists and Engineers, and the writer name is Giancoli. Okay, let me continue. So this is second rule. In this lecture, I explain the second rule, and this second rule is also known as KVL. KVL means the Kirchhoff voltage law. Loop means that this is we apply voltage loop in the complete loop. What is mean by loop, I will explain in the later section. Okay, so the statement, the sum of change in potential. So this is the main thing, is that the potential change in a circuit in a closed loop must be equal to 0. What does it mean? It means that the so this is basically energy conservation. The battery supplies energy and the resistor are components that use that energy. So the battery supplies energy, so these are utilized by the circuit components. So this energy must be equal to the energy that is being utilized, so that the total change in energy must be equal to 0. So one is giving out energy, other one is utilizing that energy. So in total energy, sum of energy or total potential change in a circuit must be equal to 0. I will explain in detail. I will explain the Kirchhoff voltage law in detail. For example, we have a battery that has, for example, 220 volt battery. Okay, so this battery supplies the potential, and this is one, we have only one resistor, for example R, so that this battery supplies 220, and this resistor also drops potential that is equal to 220, so that we can say that the total potential sum must be equal to 0, because energy is supplying by the battery 220 and the resistor utilize this 220, so that the total change of potential must be equal to 0. Okay, now I will explain in a different example. So for example, if we have a circuit, in order to apply the Kirchhoff voltage potential change, so there are two things that need to remember. Number one thing is that if we have a battery, so we have for the battery, the potential change in potential is known as the EMF. For the battery cell or battery, the change in potential is EMF, that is equal to EMF. This EMF will be positive if we move from negative towards the positive. If the direction of current, direction of the current is from negative terminal towards the positive, we are moving from negative terminal towards the positive, then the change in potential will be plus E, because we are moving from low potential to high potential. When we are moving from low potential, mean negative to positive, so that the change in potential energy or change in potential will be equal to plus E. So if we move from positive terminal towards the negative terminal, suppose if we move from positive terminal towards the negative, so the change in potential energy is equal to minus E. That gives us, because we are moving from high potential to low potential, so the change in potential must be equal to negative E, mean the minus E, because we are moving from high potential towards the low potential. Okay, now for example, if we have any resistor, if we are moving in the direction of current, if the current is moving in this direction, and we are moving from A, for example, this is A point and this is B point, so that the potential drop between VAB is equal to negative current and the value of this resistor. For example, this resistor is R, so minus IR is the potential change. But if we want to find the potential VBA, then this is equal to plus IR, that is equal to plus IR. So that for the battery, I repeat again, for the battery, the change in potential energy is plus E. If we move from negative towards the positive terminal, if we move from plus to minus, it will be minus E. For the resistor, if we move in the direction of current from A to B, so it is minus IR. If we move from B to A, so then it is equal to IR. Then it is equal to IR. In the next lecture, so I will solve this example. For example, we have a circuit and we apply Kirchhoff rules to find the current I1, I2 and I3. So in order to find the current I1, I2, so we have two loops. This is loop 1 and this is loop 2. The bottom one is the loop 2. Okay, and the outer loop is loop 3. We have 3 loops. Okay, but we apply only the current the loop in the 2 loops. Okay, KVL in the 2 loops. Okay, first we apply the KVL in the first loop, loop 1. So for the loop 1 is AHDCBA. So this is loop 1. So this is loop 1, this one, AH, then D, then C, then B, then A. This is loop 1. So how to apply the KVL in any loop? So first we take from A to H. So potential drop across A to H is VAH plus then H to D. H to D is nothing, so we can apply VH to C. VHC plus then C to B, VCB, then B to A, VBA, which is equal to 0. So the total sum is total potential drop equal to entire loop is 0. So first we apply one by one. So across VH A to H we have only one resistor. A to H we have only one resistor, that is 30 ohm. So the further resistor we have formula minus I1 and our resistor is 30 ohm. And then H to C. For H to C we apply because we only have the battery and we are moving from a negative terminal towards the positive. I again repeat, we are moving from negative terminal towards the positive. So we are moving from negative terminal towards the positive, so the potential drop is plus 45. So VH to C is only battery, that is potential is plus 45 volt. Then C to B we have 1 ohm resistor, so minus I3 is current and resistor is 1 ohm. Then finally B to A, so minus I3 and resistor is 40 ohm, which is equal to 0. Now we I explain minus 30 I1 plus 45 minus I3 minus 40 I3, which is equal to 0. So we I3 I1 plus 45 minus I3 minus 40 I3, which is equal to 0. So in order to explain this, before that we also apply KVA junction rule first. We can also apply the junction rule first. So in order to apply the junction rule, so we apply the junction rule upon this. So junction rule, okay, junction rule, I forgot to apply junction rule, so we can apply junction rule. So you can see that the I3 is entering at this junction A. So A is junction, so I1 is and I2, so moving away. So I3 is equal to I1 plus I2. So this is equation number 1. So by applying junction rule, because I3 is entering into the junction, then I1 and I2, so I3 is equal to I1 plus I2. So from loop 1 we have equation number 2. Okay, now we apply this rule to junction to loop, third loop. 1 minute, I have to write this one a rearrange so that we have space. 1 minute. Minus 40 I3 which is equal to 0. Okay, so first loop is this one, then second loop is this one, and third loop is this one. Last one is the third loop, outer loop. There is another outer loop, this one is outer loop. Okay, looping, we start from a point and then covers whole loop and then we get to the same path, same point. Okay, so outer loop, so this is loop 3. So we apply KVL to loop 3, not 2 loop, because second loop is, it's a complex circuit. So if we apply to KVL to the third loop, so it is easy for us to, we have to solve this equation. Okay, so for the loop 3, so for the loop 3 we have to apply the KVL again. So we start from A to H, VAH plus then H to E, H to E, VHE plus E to F, VE to F plus F to G, VFG, then G to A, GA, which is equal to 0. Okay, we start from A to H. So A to H is minus the, we have formula minus, because it is resistor I1 minus I1 and 30 ohm. Our resistor is 30 ohm. So because we are moving in the direction of current, so we use negative. Okay, H to E. From H to E, 20 ohm resistor is there. So from H to E, we have 20 ohm resistor. From H to E, I to E, 20 ohm resistor. Okay, so the current is I2. So as we know, we are moving against this current. We are not moving in the direction of current, but moving away. So this is plus I2, and the ohm is 30 ohm. The resistor is 20 ohm. Sorry, 20 ohm is the resistor. 20 ohm. So this is 20 ohm resistor. Okay, now VE to F. So E to F, 1 ohm. So E to F. So plus minus I2, 1 ohm, because you know that E to F is moving away against the current. So this is plus, and then F to G. So from F to G, so we are moving from positive terminal to the negative. For the battery, if we are moving from positive terminal to the negative, so it will be taken as negative, minus 80 volt. So this is minus 80 volt. Because why it is minus? Because we are moving from plus terminal to the negative, so that's why it is minus E. And then finally from G to A, so nothing is there, G to A, nothing component G to A. So so we can say this is, we can remove this one, G to A, so which is equal to 0, which is equal to 0, which is equal to, so the equation is, so we define this equation, minus 30 I1 plus 20 I2. Hello dear, so continue. So here we have, this is plus actually. Okay, now basically so we apply the KVL to the third loop. Okay, so we have this equation number, for example equation number 1 2 1 2, this is equation number 3. So this is equation number 3. From 3, let me write 3 in a more easy way. So this is minus 30 I1 plus 21 I2, and then minus it is equal to 0. So this is equation number 3 is 4. Okay, now from 3 we find I2 in terms of I1. So if we find I2 in terms of I1, so 21 I2 is equal to 80 plus 30 I1, that is equal to, so I2 is equal to 80 over 21 plus 30 over 21 I2. So I2 is equal to, so this is I1, so 80 over 21, that gives us 3.8 plus 1.4 I1. So this is equation number 4. Okay, equation number 4. So I2 is equation number 4. Okay, so from equation number 2, this one, from equation 2, this equation, from equation 2 we find equation we find I3 from this equation 2, that is equal to minus 30 I1 plus 45 minus 41 I3, which is equal to 0. So from equation 2, from equation number 2 is minus 30 I1 minus 41 I3 plus 45 is equal to 0. We find I3. So this negative minus 41 I3, so minus 30 I1 plus 45, so 41 I3 is, which is equal to 45 minus 30 I1. So I3 is equal to 45 over 41 minus 30 over 41 I1. So we solve this one, I3, which is equal to I3 is equal to 1.1 minus 0.73 I1. So this is equation number 5. Okay, now put 4 and 5, put equation 4 and equation 5 in equation 1. So equation 1 is I3 is equal to I1 plus I2. I3 is equal to I1 plus I2. So I3 is equal to I1 plus I2. So we rearrange this equation. So I1 is equal to, which is equal to I3 minus I2. So I1 is equal to I3. I3 from this equation 5, we put 1.1 minus 0.73 I1 minus I2. I2 is given. I2 is 3.8 plus 1.4 I, 3.8 and plus 1.4 I1, 1.4 I1 plus 1.4 I1. We solve this one, 1.1 minus 0.73 I1 minus 3.8 minus 1.4 I1. Okay, now we solve for I1. So I1 minus plus 0.73 I1 plus 1.4 I1, that gives us 1.1 minus 3.8. So I1, when we find I1, so we get I1 which is equal to minus 2.7 over 3.1, that gives us minus 0.87 ampere. So this is I1. Now we put I1 in equation, put I1 in equation where we have I2 and I3, where we have I2, equation 4 and equation 5. In equation 4 and equation 5, in equation 4 and equation 5. So first we write equation 4, I2 is equal to 3.8 plus 1.4 into I1. So instead of I1 we write minus 0.87 ampere. So we solve and we get I2, that is equal to 2.6 ampere. So finally we put this in 5. So equation 5 is this one, I3 is equal to 1.1 plus 0.73 I1. So we put I3 is equal to 1.1 plus 0.73 into minus 0.87 ampere. So we get, finally we get I3, that is equal to 1.7 ampere. So I again repeat, there are two or three things. One thing is that when we are moving across the resistor, so if we move from A to B, from where the current is flowing, so we use minus IR. So if we move from B to A, opposite to the current, so we use plus IR for the resistor. The potential change, we are moving from battery negative positive, we use plus E. If we move against plus to E, from high potential to low, we use minus E for the potential drop. Okay, so we solve this circuit. So basically Kirchhoff's second rule is used to solve any complex circuit in which we have battery and we have resistors, and so we can apply this rule to find the current through the resistors and to find the resistors so we have to apply this loop rule in different loops. So we have 1, 2, 3 loops, so we apply KVL in the first loop and third loop. No need to apply second loop because it's very difficult to solve for the equations for the second loop. I tried to solve first for the second loop, but it is difficult. Okay, thank you.